Okay, good evening, class. Let's start lecture. I was going to try something new today. I was going to try the classroom technology. Basically, you could run Zoom and then record using Zoom, so then somebody can watch other than inside the classroom. But anyway, so I asked for a passcode. I forgot my cell phone, so without the cell phone, I can't enable my logging into the Canvas. I'll try it next time. Okay. So for now, we're still recording it. All right. So let's continue on our lecture here. Okay? Yeah. We started on a new topic, which is to find the equation of the lines, equation of planes in 3D space. So here is a quick snapshot at the end of the lecture what we did. So basically, we have formulated the problem. We just need to figure out the solution of the problem. So the formulation of the problem is to find the plane in 3D space. So what we did is we were given, let's say, 3 points, P1, P2, P3. So let's suppose we know the coordinates of the 3 points. And we know exactly that there's a plane will be determined by the 3 points uniquely. At the same time, right, we will emphasize that the 3 points, okay, will actually not on the same line. So maybe I should add one more line here. So this P1, P2, and P3, they're not on the same line. Because if they're on the same line, then you actually can have infinite number of planes determined. So they are not on the same line, so then you would have just one plane determined by the 3 points. To find this plane equation, we introduce another variable called point P. So this point P here has the coordinates of x, y, z. It's a general variables, and the point P is on the plane. Okay? So now the objective is to find an expression that contains the 3 variables x, y, z, which will be basically an equation describing this plane in 3D space. So now let's solve this question here today, and then we'll look at a few examples. To solve this question, I'm going to bring your memory back to our first lecture when we do the review. Basically, we have looked at this problem, which is the volume of a parallelepiped. So we looked at this problem before, right? Just to quickly illustrate the problem. So the problem is basically is that if you're given 3 vectors, B, C, and then A. So if you have 3 vectors, you can form this geometry called this object, which is what we call the parallelepiped. So you get an inclined box. It's called a parallelepiped. And we looked at its volume, and we derived, and we find that its volume equal to A vector dot B vector cross C vector. So we find this solution, A dot B cross C. Okay. And this is actually the conclusion I'm going to make use of to derive the plane equation in 3D space. Okay, good. So let me ask you a very simple question now. Okay, so if this is the volume equation for the parallelepiped, then here's a question. If the vector A is in the same plane as B and C, if this vector A is in the same plane as B and C, the volume equal to what? Excellent, right? That's pretty obvious. So everything collapses. So the parallelepipeds end up with nothing. So volume should be 0. So now I'm going to use this analogy to exactly what we have done over here. So you look at the current formulation of the problem here. I have a vector P1, P2. I have a vector P1, P3. I can also construct a vector from P1 to P. So basically, I have three vectors here, right? The first vector, I can call it PB, I can call it C, just in contrast to exactly the parallelepiped. I can call P1P here as A. So now you have exactly ABC as this parallelepiped. Right? The only difference is this case set here. A is in the same plane as B and C. So then for the specific situation that we are looking for a solution at here, so then I can immediately write down, based on this formula, I can write it down P1P. Okay, so the P1P is like the vector A dot the B cross C. So B is P1, P2 cross C, which is P1, P3, equal to 0. And that's a very, very natural derivation, right? So the A dot B cross C is 0 because A is in the same plane as B and C. Then my P1P dot this cross but must be 0 because P1P is in the same plane as P1P2 and P1P3. So this is actually quite an important solution for us to work with to get the equation of plane. As a matter of fact, right? Now if you look at this current expression here, and you think about what's known, what's unknown, okay? And then you also think about the computation that's involved in this expression. And then you actually will realize the results of this dot product will give you actually an expression. So for example, right, what's known? You have the coordinates of P1, P2, P3. So you know x1, y1, z1, x3, y3, z3. Okay? The numbers are given, right? Then you can certainly write down the two vectors. So whatever vectors, once you write it down, subtract the coordinates, you get the two vectors. So you get two known vectors, and then you do the cross product, you get another known vectors, right? The vector has three components, but you will get the three values of the components. And then you dot this vector. Now this vector, the only one known is P1 coordinates. P we don't know, it's a variable x, y, z. But bottom line is, this vector here contains, if this is x, so x minus x1, y minus y1, and z minus z1, right? That's P1, P1P. And then dot, let's call this A, B, C. Right? So A, B, C will be the results of the cross product, equal to 0. Okay? Yeah. And now you calculate this dot product. According to dot product formula, you end up with A times the first component plus B times the second component and C times the third component. And then you add them together, you get an expression equal to 0. And the whole expression contains exactly the variable x, y, z. So that's the objective, right? So that basically the end results of this dot product will actually give you the plane equation. So A times x minus x1 plus B times minus y1, C times z minus z1 equal to 0. So that's a standard mathematical expression. Right? You have x, y, z on one side, you have 0 on the other side, and you have a standard math equation. And this equation is basically the plane equation in 3D space. Okay? But I'm going to talk a little more about it here. This seems to be too easy, isn't it, right? So I will actually definitely dive into this in more details. Okay? So now let's go back to this expression here. Okay? Go back to this expression. Again, we said this equation, this one here, give us the equation of the plane. So what I wanted to a little more generalize here is, let's examine this a little more here. So this vector dot this vector equal to 0. So now I want to jog your mind back to the property of a dot product. Okay? Can anybody actually tell me when two vectors dotting each other equal to 0, what is the geometric relationship between the two vectors? Colin? They are perpendicular, right? So when they are perpendicular, you get the dot product equal to 0. Or when the dot product is 0, you get they are perpendicular. So it's a necessary and sufficient condition. Right? So then I can actually conclude that this P1P is actually perpendicular to this P1P2 cross P1P3. Okay, good. So now we understand they're perpendicular. If I go back to this drawing at it here, right? What is P1, P2 cross P1, P3? So I can certainly draw it out because we have reviewed cross product. You use the right-hand rule, and you get P1, P2 cross P1, P3. That's your cross product. And this actually graphically explains why P1P is actually perpendicular to P1 to this cross product. Okay? Good. Okay, so to make it even a little bit simpler, right? To make it a little simpler, suppose that I said, I don't want to use this P1, P2 cross P1, P3, okay? I just want to find maybe a general vector that P1P that is actually perpendicular to, okay? So basically, if you look at this graph right here, I mean, you can certainly claim this is perpendicular to this, but that's just one vector, right? But in reality, how many vectors are there that this P1P is perpendicular to? Is just one, or just two, or three, or infinite? Infinite, right? So you can always draw a vector that is perpendicular to this plane you're looking for. And the n here will certainly be perpendicular to P1P. Okay? So then I think I can get rid of this cross product now. I can actually maybe make it a little simpler. I said P1P is perpendicular to n, where the n net here, okay, the n here is an arbitrary, it's arbitrary vector. Of course, it's not so arbitrary. It has to be perpendicular to the plane, or normal to the plane. Okay? I'm going to also see normal to the plane. It's the same point. Okay? So that's the n here. So in other words, when you try to find a vector that is perpendicular to P1P, you're not restricted to this cross product. You actually have a freedom. As long as you find one vector that's perpendicular to the plane, then this relationship holds. Or what relationship holds? Basically, P1P dot n equal to 0. Right? This dot product equal to 0. So you'll see why this is actually much better than restricting yourself to this cross product, right? So essentially, the idea is, if you're looking for a plane equation, right, you need to first find a vector that is perpendicular to this plane. So I'm going to let this n temporarily to be ABC. Okay, so ABC. So we'll keep it as general. So you can have any numbers you want. You put it over there, right? So now my dot product here can actually be simplified now. So the first vector is x minus x1, y minus y1, z minus z1, dot this general vector perpendicular to the plane, ABC. equal to 0. So now I'm going to expand this out again. It becomes a times x minus x1, b times y minus y1, and plus c times z minus z1. Okay, good. All right, so maybe before I proceed, let me ask you another question in here, see if you can answer this one correctly. First, be clear with the symbols I have listed here, okay? So the n here is an arbitrary vector perpendicular to the plane with certain values of a, b, c. And then over here, I have a ABC at here, capital ABC, that's calculated based on this cross product, right? So can anybody tell me what is the relationship between the capital ABC and the small letter ABC vector? What are the similarities? What are the difference? Yes. Same direction. Excellent. Then what's the difference? The magnitude. Exactly. Right? Excellent. Okay. So basically, So basically, this cross product here is a special case of this n here. Right? It's a special case. Okay. And they're only different by a scale sometimes, I would say. Right? The magnitude difference basically means it's only different by a scale. Okay. So that you got to be clear. So again, this actually gives you an idea. Is okay, if I want to find a normal vector to the plane, so this might be actually one approach, right? You could use this approach to find a vector normal to the plane. But this approach depends on what? Depends on that you have the knowledge of the coordinates of 3 points. Okay. Then you can calculate using the cross product to get a vector, capital ABC. Here's capital ABC, right? Okay. Good. So let's get back to this expression now. So now you're very clear that this ABC, small letter ABC here, represents a general vector perpendicular to the plane. Okay? And you also know that this x1, y1, z1 here is what? Is a point on the plane. Okay? So let me maybe write it down here. So this x1, y1, z1 is a point on the plane. And then this A, B, C, okay, half bracket, and this is a vector, right, A, B, C, and this is a general vector, okay, normal to the plane. So these two information, right, you have to be crystal clear what they are, because they are basically the fundamental information you need to create the plane equation in 3D space. Good. So let me get back to this equation here, right, this plane equation. If you have an exam question asking for plane equation, you can actually stop here. You don't need to do any further steps, and you get 100% if you get it right. Okay? Yeah. Now, of course, for simplicity, you can further write it a little bit more. Basically, what we could do is we multiply A, B, C into the bracket. So we get AX minus AX1 plus B1 minus BY1, then CZ, CZ1 equal to 0. And then we can simplify this a little bit more because we know x1, y1, z1. We also know a, b, c. Then, of course, I'm assuming you know, right? For certain question, you have to try to find it out based on given conditions. Sometimes it's not directly given to you, a, b, c. Okay. So you can combine the constant terms together. So those three are constant terms. And then you can move the constant terms to the right side of the equal sign. So then I end up with ax plus by plus cz equal to ax1 plus by1 plus cz1. So the whole equation is simplified a little bit. It does look a little bit different now, but it's still the same equation. And then the whole right side here, bear in mind, they are constants. So when you add them together, you get a number, basically. Okay, you get a number. So the number, let's call it a d. Okay, let's call this number d. Then the whole equation becomes even simpler by its look. So ax plus by plus cz equal to a constant d. So basically what I'm trying to illustrate it here is when we talk about plane equation, you, in terms of format or in terms of how it looks like, you can have it this way. Okay? You can have it this way, or you can have it this way. It's the same thing. Okay? So this second one here, more or less, is a derived expression, right, based on the first one. Okay, so now let me ask you some questions, and let's see if you understand, have a initial understanding of this plane equation, right? Yeah. So let's use this one for the current question here. Okay. The question is, suppose that you have a plane, right, which passes through the origin. So you have an XYZ coordinate system, and it passes through the origin. So the question here is, if this plane passes through origin, what is that d value? Okay? What's the d value? Let's say I have to give you a multiple choice question A here. It could be anything. B here. Does not exist. C here, this is 0. So let me see your hands. Which one would that be? You can use 1 finger for A, 2 finger for B, and then 3 finger for C. Okay, good. Right, excellent. Okay, so what did you guys do to get a 0 here? What did you do to get a 0? Anybody? Well, you must have a way to do it. Yes, go ahead. Exactly, right? So you substitute the coordinates value into the plane equation, and you get a d value. Okay? That's a very important skill, I can tell you. It seems to be very simple. Sometimes you need that simple technique to get you something. Okay? So basically, x, y, z here, what you have already understand is they are coordinates, right? They are coordinates for any point on the plane. If origin is one of the points, then, one of the points on the plane, then you're substituting 0, 0, 0 here, right? If you do have any other points, and you can certainly do the same thing, right? Okay, very good. Alternatively, I actually could ask you this following question here. Okay, here's another simple example. Let's see. Okay, so this time I'm giving you a plane. Okay? I'm giving you the plane 3x plus 2y plus 6z equal to 4. Good. So now I'm going to ask a question here. There's going to be no set of answers. Can you give me a point? Can you give me the point, meaning give me the coordinate associated with the point? Can you give me a point on that plane? And don't give me any weird points. Just give me a very easy to find points. 0, 2, 0. 0, 2, 0. Yes. Right? You plug a 0, 0 here, and 2 times 2 is 4. So that satisfies the equation. Very good. So that's actually exactly what I'm trying to show you here. Right? That's very easy. Why is it easy? Because what he just did is he let 2 of the variables to be 0, and then solve for sorry, what is that right here? This is y here, right? And solve for the other variable, right? For the last variable, and you end up with a 2. Okay. So by that extension, can anybody give me another maybe easy to find points? So 0, 2, 0 is 1. What about others? Yes? 0, 0, and what? 2/3. Yes. Okay? Yeah. It's not as integer as this one, but yes, it is, right? Yeah. So this time you're setting x, y to be 0, you solve for the z. Very good. All right, so this is exactly the way you can find points on the plane. The reason often you might think, what's the point of doing this, right? Because when you solve a question, you're given a plane equation, and then you're asked to get some other information, okay, to solve certain questions. And often in time, you probably cannot get exactly the way the solution to get the answer. But what you could do, right, is you can do even something like this right from the beginning. Basically, those are easy, lower hanging fruit you can get right away. Say, okay, I have a plane, so maybe I can figure out a couple points on the plane. Then I can make use of it, right, for whatever purpose next. Okay. So once you get a couple points, maybe you expand your, inspire you in some way, and say, oh, okay, I could do this, I could do that, and then one thing leads to another, and you find a solution. Right? So that's my point. Okay. So easy, but lower hanging fruit, right? It doesn't hurt at all, and I often give you partial points. You write it down, you get 1 or 2 points already. Right? So that's why I encourage you to do these things right away. Okay. Good. So now let's look at an example. Okay, a couple examples here. Okay. I'll give you a plane. 3x plus y plus 3z equal to 5. And then I'll also give you a vector. Okay. Then the question here is, okay, oftentimes this will be a multiple choice maybe. Okay. What is the geometric relationship between this plane and this vector? So now I'll explain a little bit what does geometric relationship means, right, between the plane and a vector. Now, of course, first of all, if you have a software, you have MATLAB or Maple or any other engineering computation tool, you can always plot this plane. You can also plot the vector. Chances are, once you plot them out, and you can immediately tell what are their geometric relationship, right? But geometric relationship essentially means if you have a plane at here, and then imagine the vector. So the vector could be, right, direct on the top of the plane. Right? So if this is a plane, the vector is direct on the top. And if you imagine there's a line coming through the vector, and the line will never touch the plane. Okay, so that's one geometric relationship. And this geometric relationship, what we call this, the vector is parallel to the plane. So the vector not, in any nature, will not intersect the plane, basically. Okay? So this is, say, V is parallel to the plane. Okay, that's one type of relationship. Right? Okay. Another type of relationship is that basically this is a special relationship. So the vector here is perpendicular. Now my drawing is a little bit exaggerated. I mean, the vector not necessarily is intersecting the plane. The vector could be anywhere, right, in 3D space, because vectors are free. Okay, you can move it around. Okay. So that's a second special relationship. This V, right, is perpendicular to the plane. And the third one, the vector probably in the arbitrary location, but if you extend it, the vector, right, will form an angle, but not 90 degree with the plane. So that's your third geometry. Right? So this V here forms a certain angle, but the angle is not 90 degree. But apparently you can see these parallel and perpendicular are kind of two special geometric relationship between this vector and the plane. Okay. Good? So that's the question here. Basically, given this plane and this vector, what would be a quickest way, right, or shortcut to find this geometric relationship? Most probably, you know, I'm looking for either this or that, right? Yeah. So this essentially kind of back to our review on the concept of a dot product and the cross product. All right? Yeah. So oftentimes this really needs a little bit. You need to sometimes think backwards, basically. Okay? Yeah. So for example, right? Thinking backward means based on the review, you know, as we did in the previous example, we used a dot product, and we also use the nature when dot product equal to 0, the two vectors are perpendicular to each other, right? Okay, so in this case here, you know, I don't have two vectors. I only have one vector here, right? So suppose if I want to use a dot product, the nature of the dot product, the property, okay? So then what do I do? So I need to find another vector, right? But that vector is not going to be arbitrary vector. It has to be something associated with the plane. So this actually sort of trying to get back to our original plane equation. If you look at the plane's equations, coefficient for x, y, z, a, b, c, the coefficients here. Remember what A, B, C's are? Right? It's a vector perpendicular to the plane. So I think that can give me some sort of information, right? So I'm going to draw a vector perpendicular to the plane. And before even I do anything, I can just actually write it down. The n here equal to, what's the plane equation? 1, 1, 3. So I haven't done anything yet. I'm just writing it down. I just wrote down a vector that is perpendicular to the plane based on the given plane equation. Okay, you got 2 points maybe, right? For a 15 points question, for example. Right? So now from here, and then you can look at, of course, without the computer, I cannot know how exactly this V will look like. Okay? So suppose the V looks like this, whatever, in the 3D space, right? Now I can actually try to use the dot product. So let's just try it out, right? So what if n dot V is 0? Who knows, right? So let's calculate it. Okay? Let's calculate this dot product first, see what the value is. Okay, so you calculate the dot product. Okay, n is 1, 1, 3, and then V is, what's V again? 1, 2, negative 1. Okay, so you calculate dot product. So 1 times 1 is 1. 1 times 2 is 2. And then 3 times negative 1 is negative 3. The whole thing is 0. Right? That's nice. I got a dot product equal to 0. So that leads you to the next question. So what does it mean when this n dot V equal to 0? That means what? The n is perpendicular to the V. So if n is perpendicular to the V, so what's the geometric relationship between the V, vector V, and the plane? Parallel. Right? So excellent. So that's a logical decision, right? Logical derivation based on this dot product's value. So that's why you see V is parallel to the plane. Okay, very good. Good. Maybe I'll just ask a question like this. So suppose, things probably running a battery sometimes. Okay. So suppose, let's see, suppose the V is perpendicular to the plane, right? Or suppose that the dot product is not zero. Okay? Suppose not zero. So what else could you do? What if the cross product is zero? What does that mean? What if this cross product is zero? N cross V is zero. N cross V is zero means what? Yes, go ahead. What pair, sorry? You mean V is parallel to N, or V is parallel to the plane? The two vectors parallel to each other, right? Good. So the two parallel to each other means V is what? To the plane? Perpendicular. Okay? Yeah. You see, that simple calculation of either dot product or cross product will actually reveal a critical relationship between this vector V and the plane. Okay? So, but not for this question, right? This is dot product zero. Okay? But cross product, the usage cross product, right, is one example how you can reveal the other relationship. Good? So for now, often in time, I encourage, you need to have a critical thinking. You have reviewed some of the basic concept. Many of the question basically is making use of the results of that review, right? So be open, right? If you don't know how to proceed with the current question, just kind of go back to the question. Can I use this conclusion, dot product? Can I use that conclusion, right, a cross product? Yeah. Once you tried it out, you see, oh yes, it does work, right? That's sort of how you can initiate the solving of a certain question. Okay, this second example here is a very good example and also very common example. You probably will see in assignments, also quiz. Okay. This type of example, I usually categorize it as a distance type of question. Okay. So the question here is, we have a plane given. We also have a point given. Okay. And then the question is to find the shortest distance. The shortest distance from this point S, okay, to the plane. And you probably will see when we learn line, after we learn equation lines in 3D space, we'll have a similar examples, from a point in 3D space to the line. What's the shortest distance? Right? So this one here is from the point to a plane. If I have to illustrate this, essentially you can draw a plane in 3D space. Then you can draw the S, okay, as illustratively the location of S. Then you're looking for, right, is this shorter distance from S to the plane. And the current plane, of course, is given already, 3x plus 2y plus 6z equal to 6. Okay, good. There are actually multiple different ways to solve these things, okay? Yeah. But for now, what I'm going to encourage you to do is to get used to basically how to connect the concept that we have reviewed, or the concept related to dot product, cross product, right? Back to this kind of a question right here, all right? Yeah. But again, as I mentioned in the other question, even if you don't know what to do, okay, so you can always actually write down a few things first to help you out, maybe. So what can I write down at this initial stage? Okay, write down the obvious ones to help us based on the given condition. So here's a plane equation, right? So maybe I can write down something based on the given condition, which is the plane equation. What could we write? Yes? Sorry, come again? N? Yes, excellent, right? So you can certainly write down a vector that is normal to the plane, which is the coefficient of x, y, z. Okay, excellent. So I write it down n, 3, 2, and 6. Good, thank you. 3 to 6 is n. Now, of course, you might want to argue, can I write down a different normal vector to the plane? Yes, you can. Okay, so the bottom line is yes, you can. To give you an example, that you could write a different. For example, right? For example, let's see if my plane equation given you is 2, 4, and 6. Let's say the coefficient is here is 2, 4, 6. So instead of writing 2, 4, 6, you could write what? 2, 1, 2, 3. Right? So they're all the same direction. There's just scale difference, right? I think 1, 2, 3 probably is easier to work with, at least to compute, right, than 2, 4, 6. But really, they don't make a difference at all. Right? Yeah. But this one, there's no common factor, so I don't think you have any other simpler values to present. Okay, so that's one easy thing to write it down. Good. What other things we could write it down? Right, we could write it down here. Anybody? Right. Any hidden information that you can actually extract from the given condition? Let's hear from that. Sorry, let's hear from the middle one. No, you. Yes. Excellent. You pick a point P on the plane, right? So, I don't know where it is. I will just pick a point P on the plane. Okay. So now this is where things differentiate. You pick this P, and he picks the other P, right, different point P. Okay. But as I said, you can certainly pick an easier point P. So what would be an easier point P over here? Anybody give me a very easy point P? Yeah, 0, 0, 1. Excellent. Okay, for the benefit of information, can anybody give me another point P? 2, 0, 0. Yes. Good. All right. So that's the point. You can pick a point P here. Okay. So now all of a sudden you have more things on the paper, right, than the original just a plane and a point S. Okay. So from here, I think it requires a little bit of training, also a little bit critical thinking now, right? Yeah. So I'm going to lead you to give you a hint. Back to my conclusion when we do the review of a dot product. Okay? So when I do the dot product, I have emphasized a lot that when you have a vector dot a unit vector, what does that give you? Right, what's the physical meaning? Yes, go ahead. Magnitude what? When you have a vector and then dot a unit vector. Let's call this as A here. So when you have an A dot U hat. Yeah, I want the very exact precise wording. Yes, go ahead. Exactly, right? The dot product gives you the length of the projection, okay, or projected vector. Okay? So, and then you back to the drawing at it here. If this is projection, right? So projection means from here to here, right? This black length, and this one here give you a dot U hat. Right? That's the length of the projection. Okay. And as a matter of fact, I mean, length of projection, if you look at this relationship here, I mean, this is like a distance, isn't it, right? It's a distance. Okay? And it's also the shorter distance from this point to this line here. So that's why I actually emphasized a little bit at that time the concept of dot product, A dot U hat, or any vector dot a unit vector, right, is a very important information that we can actually make use of in finding some of the critical pieces of puzzle here. So you look at the current question, where exactly we're looking for is a distance, right? Is there any way I can use this nature of vector dot U hat to give me that short distance? And that's basically called critical. How can I make use of this solution here, this available property here, right, to help me with this question? So if I want to use this, I guess I need a direction, or I need a U hat, right? So if you look at the U hat is in which direction? U hat is in the direction exactly, it's in the direction of what? Yes, right? It's in the direction of the length you're looking for. Okay? So currently, what is the length? This is the length here, right? The D. Then what direction can I use to represent this direction? N hat. Excellent, right? So sorry. Good. And N hat is the one perpendicular to the plane. And that's the direction in the direction of the distance D. So I got this part figured out now. I guess now I need to figure out A out of here for me to do the dot product. So can you give me a vector A? Yes, go ahead. P, just P? But this is not a vector. This is the coordinates. I need a vector here, right? I need a vector. Colin.
If you connected and drew vector PS, so from P to that.
Very good. Right. So that is the candidate, right? You create a vector. You create a PS vector here. Okay? So you could also SP, that's fine, but PS. Right? So now you can see geometrically, right? You have PS here, you have N here, you PS dot N hat, exactly give you the D. And this whole question will become so simple, right? So PS dot N hat is the D. So I guess the next few steps will be much easier to do once you write this down, because you already have P and you already have S, so you can easily write down PS using the coordinate of S minus the coordinate of P, and that gives you S is 113, so 113 minus coordinate of P minus 0, minus 0, minus 1, and the whole thing is 112. So PS is 112, and then your N hat, right? Because N hat needs one more step out of here. I don't have an N hat yet, but what do I have? I have N. How can I get N hat? You normalize that with its length, you get the N hat. Okay, so this one here, you normalize that. N here is 3, 2, 6. So you divide its magnitude or length. Magnitude basically is 3 squared plus 2 squared plus 6 squared, and then square root everything. You end up with just a 9 plus 4 plus 36. If you add them together, so that's a 13 plus 36, 49. Square root of 49 gives you a 7. So nicely round it to 7. So then you get 112 dot 326 over 7. So the rest of it is just to calculate the dot product. You end up with just 17 over 7. Okay. That's the result. The shorter distance from this point S to the given plane over there. Okay. Good. So we're right on the time. So we'll have see a couple more examples on this and a little bit of the summary on the plane here. But that's the gist of plane in terms of today. Okay. Any questions? Feel free to come over.